Hello and welcome. Let's talk about some of the data analysis for experiment 5, activity 3. So let's say you've done your first calculation on CH4 at HF and whatever basis set. I have the result here at HF. So just seeing what method I actually ran. I just opened some random file on CH4 I'd already completed. And the way we're going to go about getting some information here, so let's see what we're told to do. So write the bond lengths and angles. That's easy enough to do from the structure above. Find the energies of the occupied MOs of CH4 and EV. Ignore the virtual orbitals, and then record the electronic energy. Okay, so some of the things here. Let's actually go back to the beginning. So like if you choose the arrow, like click on this arrow here, then you can click on the atom, shows you the bond length, and you can click on atoms in whatever order you want to get the bond angle in, shows you the bond angle. So close to 109.5, not exactly 109.5. And then if you want to get the electronic energy, that's going to be here. It'll be the R method energy. So if you're talking B3 lip, it'll be the R B3 lip energy for when you do the B3 lip calculation. When it's CCSD, it'll be the R CCSD energy. Okay, and so then if you want to get, so that should give you basically everything except for the energies of the MOs. So how do we get the energies of the MOs? Well, there's no easy way that I know of anywhere else in the results method other than in the raw output. So just click onto the raw output. I'd already opened it earlier, so it's here. Scroll all the way to the bottom, and there's another video where I go through the raw output file. So it's like using WebMO, I think part 3 goes through some more information in the output file. But if we scroll to the very end, we did an opt plus freq. So it should be the frequency calculation output. And the way you can usually tell you have the frequency calculation output is you see your thermal corrections. Here you'll see like a listing of your vibrational frequencies. And if you didn't do a frequency calculation, you wouldn't see it, this type of data here. Okay, and so usually if you go upward before you do the frequency calculation, before the method does a calculation, it like runs a quick geometry optimization and gives like the energies of the MO. So what we're looking for here is the like it's mentioning the occupied orbitals and the virtual orbitals. And then it's going through requesting convergence, and it's going through and like checking for this convergence, and then once it's finished, it gives you the population analysis. So you see here your your 5 orbitals and then the virtual orbitals. Okay, and so here's that really stable orbital. This is that 1s core. Then this will be the 2s overlapping with the hydrogen atoms. And then the next orbital, you can tell this because it's the triply degenerate set. This is the p orbitals of carbon overlapping with the hydrogen 1s orbitals. And so these are our orbital energies. These are in EVs. These are in electron volts. Okay, so those are the numbers that you're going to be recording here. And then to scale, you're going to have your MO diagram, really stable orbital, then a 2s, and then like 3 lines for a p. Okay, and so then moving on to part B, where you ran the calculation on CH4 radical cation, but just the energy calculation. What you're going to do here, let's see what we're extracting. So we're going to record just the electronic energy. It might be worthwhile for you to make sure the geometry is still identical. Your bond lengths and angles should be identical to A. Otherwise, and we truly didn't do an energy calculation here, we did something else. And then we do want to use the results from A, so it's important that we use the exact same structure we found in part A and run part B. Here we just need the electronic energy. If we do the electronic energy minus the electronic energy, so do the electronic energy of B minus that from part A, that should reveal the ionization energy, the energy it took to remove that electron. So loss of an electron from methane without a change in geometry corresponds to the vertical ionization energy. calculate the ionization energy by taking the difference of the electronic energies of the radical cation and CH4, convert this quantity to electron volts. And then for an electron to be removed from a more stable orbital, more energy must be absorbed by CH4. So the energy you first calculate would be the electron being removed from the highest occupied molecular orbital. So in order for an electron to be ejected from a lower occupied MO, then you just simply have to add how much more energy that orbital was stabilized by. So take the difference of energy between the 2s, 1s overlap of carbon in the H atoms. So take the highest occupied set of MOs minus the lower unoccupied MO. Take that difference, see how much energy that is, and add that on to your ionization energy that you found from just comparison of the electronic energies. So use the MO energies to determine how much more energy is required to eject an electron from the next lowest orbital and then from that really stable 1s orbital of carbon. And you can repeat this analysis by doing the full optimization, allowing the structure to optimize. You still just need only the electronic energy, and then you're doing the same sort of analysis as we did above for the next two lower orbitals in terms of their stabilization. The next two more stable orbitals take more energy to eject an electron. And then, we can compare different methods and see how they compare. And so that, in a nutshell, is the analysis behind activity 3. So the key here is making sure that you use the same method and basis set throughout your method, and that when you're doing the single point energy calculation that you choose the optimized structure for CH4, and then in the third calculation you allow the geometry to optimize for that calculation. Okay, that's all for this video.